Alright, in our final video for section 4.4, we're going to talk about oblique asymptotes. This is the final type that we're going to be discussing in this class. There are some other asymptotes that are quadratic in those types, but we're not going to be dealing with those in this class. You're going to be dealing with vertical, horizontal, and oblique. So an oblique asymptote, we have our numerator, p value, or p function, is exactly one more than the degree of q. So that means the top exponent has to be one more than the bottom. Now in order for us to find the oblique asymptote, we have to use polynomial long division. That means the stuff that we did in the section 8.3 earlier earlier this week. So I'm going to review this. We're going to take some of these and find the horizontal asymptotes using the polynomial long division, and then we'll write those down. So when you have an asymptote on a function, you can either have vertical and horizontal asymptotes, or you can have vertical and oblique asymptotes. You can't have both because oblique asymptotes deals with the powers as well as the horizontal ones deal with the powers. So since this type of asymptote is dealing with the powers, the highest powers on here, the degree of the polynomial, you can either have horizontal or you can have oblique. You can't have both because there are three options. The power on the top is more, which is oblique. The power on the top is less, which is horizontal, or the power on the top and the bottom are the same, which is also horizontal. So those are your three choices. Now, if the power on the top is more than one, then you're not going to have an oblique linear asymptote. So we have to have exactly one more power. So here we have a power of 2, here we have a power of 1, so I'm going to be doing my long division, polynomial long division to find my asymptote. Okay, so what happens is my divisor, what I get here, is going to be my asymptote, except for the remainder. The remainder is not part of the asymptote. So if I'm dividing here, my first step was to take my first term, 8x squared, and divide it by my lead term here, 4x, to determine my first divisor here. So that would be 2x. So I put 2x up here, and then we distribute that over both of these terms and write it down underneath here. So 8x squared for the first one minus 2x. Now I subtract. 8x squareds are gone. This becomes positive, so that gives me 28x. We bring the 7 down, actually negative 7, and we divide the 28x divided by 4x. So we get 7 here. So in this case, the answer is 7, and that goes in completely evenly. So we have 28x minus 7. So that means we have no remainder. So if we have no remainder, then what this is actually, since it went in evenly, is that this is the same. That means we could have factored this, basically. If it went in evenly, that means the top factors into 2x plus 7 and 4x minus 1. And the bottom is 4x minus 1. So that means it reduces to this. We didn't reduce it all the way, so that means this is the same as 2x plus 7. So this function and this function are going to look the same except for the hole. There is a hole missing because of the 4x minus 1. So this is actually a graph of a line. It's not going to have a oblique asymptote. It is the oblique asymptote. It's the same as the asymptote except for that hole. There's a hole at 4x minus 1 equals 0, because that's going to be this place where it's undefined. So 4x equals 1, x equals 1/4. So that means that there's a hole at 1/4, but it's going to graph as a line. So if I look at the graph of this function, let's clear off this one here. See if this is a function we had before in a previous one. If we were to graph this one, 8x squared plus 26x minus 7 divided by 4x minus 1. All right, and we're going to do our zoom decimal 4 so we can see the missing point, hopefully. We can't see the missing point because we're too high there, but it looks like a straight line, and we're not able to see the missing point because of the window. So if we did a trace on this, we can then go back to 1/4. Well, we can't do that because it goes by tenths. So we miss it anyway. We won't get to 0.25, so we're going to miss the hole anyway by looking at it that way. So we could try evaluating it. It says find the value at 0.25. It should be, there is no value because it's undefined there. But in this case, since it went in evenly, there is no asymptote. There is no oblique asymptote. I'm sorry, I had a little cough there. So let's look at this next one. I'm sure that this one doesn't go in evenly. So if we were to change this problem just a little bit and make this number not -7, if this was just +7, then we would have had a remainder, and our oblique asymptote would have been 2x plus 7. So if I were to change this function just a little bit, just a tad, just a little bit here, if I were just to change it a little bit and make it, let's move this one down. If I were to make it r of x equals 8x squared plus 26x plus 7 instead of -7, it has to be just something different than that, because this one goes in evenly on this one. But if we just change this, so the last step would give us a remainder, that means that then 2x plus 7 would be our horizontal asymptote. In this case, when we did the division, we would get, so when we do the division, if we looked at that first example, we'd get 2x plus 7 for this division. But then we would end up with, let's move this down a little bit more. But we would end up with a constant, whoops, we'll put a plus here. So when we got down to here and we subtracted, it would be a plus 7 here and another plus 7. So we'd have a remainder here of 14, or we'd write it 2x. So when we got that division, we get 2x plus 7 plus 14 over 4x minus 1. So this would be our polynomial division. Our oblique asymptote would be y equals 2x plus 7. We just eliminate the remainder, and the rest of it is our oblique asymptote. So we just take whatever we got here and that would be our oblique asymptote. So on this example, if I changed it a little bit to +7, we'd get a remainder. If that occurs, then we get an oblique asymptote. So let's try that on this one. I think that we're going to get an oblique asymptote here. This one's a little bit more challenging because we have some missing terms, right? So we have x to the second minus 5x minus 14 divided into x cubed plus 1. Well, I'm going to put in some missing terms here. I'm going to say there aren't any x squareds, there aren't any x's, then we have the plus 1. So I'm going to do this division. Now, we haven't done one like this before. There's 3 terms here. So we still look at the first term here and the first term here, and we divide. So we take our x cubed term, that's the first term here, and we divide it by our lead term here. Lead divided by lead, so we get x squared. So that's going to be x. That's going to be my first term in my divisor. So when we do our distributive property here, we got to actually do it 3 times. So we get x cubed for the first term minus 5x squared minus 14x. And we need to subtract all 3 of those terms because there's 3 of them in what we're dividing by. So this goes away, this becomes positive 5, and this becomes positive 14. And then we bring down our 1, and we divide one more time. So then what we do is we take our lead term here, 5x squared, and our lead term there, x squared, and we divide, we get 5. So this is going to be a plus 5 here. And we distribute. So we're going to distribute 3 times. So 5 times that is 5x squared. 5 times 5, actually negative 5, so it's negative 25x. And 5 times 14 is negative 20 plus 270, negative 70. We're going to subtract. This goes away. This becomes positive, so we get 39x, and this becomes positive, so we get 71. Now this is our remainder because x squared doesn't go into this. This is our remainder, but that's not necessary for our horizontal or our oblique asymptote. The only thing that matters here, so our answer here is going to be plus 39x plus 71 over x squared minus 5x minus 14. In this case, our oblique asymptote is y equals x plus 5. We only take this part of the solution of the polynomial division to get our oblique asymptote.